So, welcome to the second lecture, Introduction to Lattice Boltzmann Methods. Still on the basic theory of the Boltzmann equation. Today we talk about the equilibrium function. And this derives from last week's derivation of the ether theorem. So the content of today is going to the discussing the equilibrium function. Then we introduce simple approximation for the collision operator moments, and we also introduce orthogonality. Somebody coming. Okay, let's recall. Let me do it this way. Let's recall last lecture's ether theorem, where we had ether being equal to the integral over f, the distribution functions, times the logarithm of the distribution functions dx and dx. So this is over the entire space and over all the velocities. And for the purpose of some simplifications, we assume that f is non-dimensional, or that we non-dimensionalized it. Then dh by dt, so the time derivative of this we have derived is smaller or larger than 0. And then there is, of course, this special case where this time derivative is equal to 0, so where the behavior of the distribution function does no longer change, so the distribution function would stay the same, so there would be only one, and this is what we define as equilibrium. Okay, so equilibrium is the state at which the ether function does no longer change. So, and we derived last week that dh by dt, by putting everything into it, is 1/4 the integral over the collision kernel B in F1, F2 after collision, F1 times F2 after collision, minus F1, F2 before collision. So we always need two distribution functions because we are colliding two particles. These are binary collisions, times the ln of F1, F2 minus ln F1 after collision, F2 after collision, and this all integrated over dx1, dx2, so the velocities of both particles over all directions and over the entire space. Okay, and again we said that F1 dash is equal to F1 at the microscopic velocity C1, and this of course for all the different parts, so the same thing for F2. So, and the important thing that we discovered, or the reason why this goes in one direction, is that F1 after collision, F2 after collision, minus F1, F2 before collision into ln F1, F2 minus ln F1 after collision, F2 after collision. This is smaller or equal than 0. Always, because the logarithm is monotonic. always means at every point. Yeah? So up here for the h, we had the integral, not the h, the ether. We had the integral over the entire space over all the velocities. But we see that this integral is smaller or equal to 0 because the integrand is always smaller or equal to 0. Yeah? So this will be 0 only if it is 0 everywhere, right? So this is the important thing. So we look at d eta by dt is equal to 0. This is where we want to look at it. This is only the case if for all our velocities, xc1, xc2, and of course the other ones, the after collision versions, for all of them, f1 dash f2 dash minus f1, f2 if this is equal to 0 everywhere. So, okay. This means they need to be the same, obviously. And this now can also be expressed in a little bit a different way, which we call now equation 2.1. Because we have here a product of two distribution functions, yeah? And the only thing that we really know about the distribution functions are their conservation laws. Yeah, so we know they have to have a specific. They would have a given mass which integrates to 1. They have a momentum and they have an energy. Yeah. So and now the problem is we have the product of the two on both sides, and in order to separate them, what we do is we take the logarithm, yeah, because when we take the logarithm, we get the logarithm of the first plus the logarithm of the second is equal to the logarithm of the same distribution functions before the collision. So now it was Maxwell's assumption that he could somehow generate a function that fulfills these conditions for given conservation laws, and this was then proved by Boltzmann in 1817 too. We look only at a very rough sketch now, or more or less only give the results. So Boltzmann proved Maxwell's conjecture that the equilibrium looks like this. Is of the form that the logarithm of f equilibrium can be expressed as A plus a vector B scalar product on xi plus c xi scalar product by itself. Yeah, so the reason for this conjecture was, of course, that he wanted to see, say, 3 different things that are conserved, namely the mass, yeah, that you see here, the momentum in principle that you have here, and this would be the energy, and they would be conserved. So the way we see that, at least this is not inconsistent, even though I'm not going to prove that this is the only solution, but I'm now showing that this is the solution, and it is also the only solution. But let's just make it relatively simple. We look at the left-hand side of equation 2.1, where we have ln f1 after collision plus brackets ln f2 after collision. So this would now be 2a plus b. Now comes the first velocity plus the second velocity after collision plus c. So we just sum this up, xc1 times xc1, so after collision, plus xc2 after collision times xc2 after collision. So where you see that the first again is now the sum of the energies of the two the sum of the momentum of the two, yeah, plus the sum of the energy of the two, yeah, times again. Okay, so forgot here this scalar product, right? So of course, I mean, times these constants. Yeah, you know, you cannot sum up momentum in energy. Yeah, so there must always be some constant in front of it in order to make it dimensionally consistent, right? But this is the basic idea. And if you look at the right-hand side of 2.1, we have, of course, ln f1 plus ln f2, and this is 2a, and we see that would be the same. So we are conserving the number of particles. This is what it means. Plus b comes now xc1 plus xc2. So this is the momentum before collision. And you see this is the same momentum as after collision. Plus xc1 before collision, and the second energy, the energy of the particles before collision, and this again is the same. So this is here our conservation of momentum, and this is our conservation of energy. So these things have to be the same in the distribution, and this is what this form of the distribution function does. So because they are here the same for the left-hand side and the right-hand side, we have conservation of these quantities, and this gives us then the equilibrium distribution function, e by the power of a and e by the power of b times c plus c. So, very sorry. So now this is the equilibrium function that we are apparently getting out. So, okay, why is this important? Why do we want to know the equilibrium distribution function? So this is where the state of the distribution function is going to if we let the molecules do whatever they do, right? Now, if we want to study this, for example, in a simulation, we can, of course, follow all the particles, and this is what they would do. Yeah? But in order to do this, we have to follow all the particles. I mean, we have to simulate all the collisions. Yeah? To distinguish between the particles, we have to track the particles, and so on and so on. And then that would be the outcome. And now the idea behind this mesoscopic modeling is to say, wait a minute, I don't want to do this because, and I don't need to do this because I already know what it does. Yeah? So instead of following all the particles and see what they would do, we simply say we have an equilibrium state, and whatever we do is we're getting closer to this equilibrium state. Now, getting closer to this equilibrium state can, of course, mean a lot, and this is not at all clear how this works, but right now we will introduce more or less the simplest way of doing this using the so-called single relaxation time collision, or approximation. Okay, or this is also called BGK operator. Okay, it's called BGK operator because it was introduced by Nagar, Cross, and Krug in 1954. So okay, what I just said, the original collision integral is difficult to solve. This is why we want to get rid of it. And we get rid of it by recognizing that what collision does is it is driving the distribution towards an equilibrium, or the equilibrium. And the good thing is we know what the equilibrium looks like, yeah, because we derived this from the ether theory. So now the BGK made the following model. They made the following model. The collision operator is the change of df by dt only due to collision. This is why we write here collision, yeah, so because it also changes due to advection, yeah, so only because of collision. This is described as the equilibrium function minus the state, the pre-collision state, yeah, so equilibrium function minus pre-collision state is the distance between the equilibrium and the state that we enter, and we divide this by tau. Yeah? And this tau is called the relaxation time. And it is related to the mean free mean time between collisions. So a basic idea that you could have in your mind is the following, that when particles have collided, they first undergo an advection step, so they move in the direction where they were moving, yeah? And after moving, because there are gradients in the conserved quantities, they are no longer in equilibrium. And once they hit another particle, the outcome of this collision is random, and because it is random, it will on average go to equilibrium. So the idea is that at the collision time, so after the time that it took from one collision to another collision, it is set to equilibrium again. So the time that it needs to go from non-equilibrium to equilibrium is related to the time that it needs to travel between two collisions, and this is the collision time, and this is what we call tau. So the after collision state, F after collision, can then be expressed as doing the integral over the time derivative, and this then looks like this. So what I'm over a time increment that I call now delta t, later, this is F equilibrium minus F over tau, and this is integrated over tau, over t, okay, now I can't write t again because I use t I cannot write t again because I used t as the bounds of the integral, yeah? So this is okay, I should write, it's better write t with a modified t, yeah? So this collision operator is conservative. I mean, as conservative as it's supposed to be, namely it conserves the mass, which we can check by taking the integral over the entire velocity space, f eq minus f over tau. So tau, by the way, tau here is a constant, yeah? Or it could depend on temperature and density in principle, yeah? But now we assume it to be a constant here, so the time between flights of collisions. So if we integrate this thing over the entire velocity space, yeah, if we integrate f over the entire velocity space, we get the density of particles. Yeah, the density of particles of the equilibrium and the function itself is the same. Yeah, I mean the number of particles. Yeah, there's a single particle distribution function. Yeah, so it's one particle in f and one particle in feq. So if we do this integral for both of them and subtract them, we of course get 0, and this means it conserves mass. The same thing is true for momentum. So we get momentum, or the change of momentum due to this operator would be the operator times xi, and this integrated over xi. So this, of course, okay, maybe I should say this is not a scalar product. This is why I now don't write this point. So this, of course, has three components. Yeah? You integrate over xi1, xi, upsilon, and theta, as we introduced, and all of them are 0. Yeah, because the equilibrium function has the same momentum as the incoming. Yeah? And the same would be true for energy. So in order to get energy out of this, is we multiply by xi xi scalar product xi and integrate over xi, and this again is 0. So these things we have already introduced last time. These guys are called the moments. And they are extremely important for understanding kinetic theory and the Lattice Boltzmann method in particular. Okay, let's talk about moments. Okay, in general, whatever we call a moment is an integral, or I often say integral properties. So integral properties means it is something that comes out of an integral. Yeah? So you sum up all the atoms in a stone to get the weight of the stone, right? So the weight of the stone, the mass of a stone, is a moment of the distribution of atoms in the stone. Yeah? So it's an integral property of a distribution. And what it does for us is giving us the transformation between microscopic variables and macroscopic variables. Yeah? So as I just said, we're counting atoms. So we have an atomistic description, and we take this to a continuous macroscopic description. I mean, this is more or less the reason why it works in the first place, that even though we know that everything is made up of particles, what we do in school and in university, we always look at things in terms of a continuum. Yeah? Yeah? And the reason why this works is we can compute moments of this distribution of the molecules, yeah, and this is something then that acts as a macroscopic variable which is continuous in space. So this is what is behind this, and now let us go to the make a brief but deep dive in the definition of how we classically describe moments, and we come to the point that at the end of the day, nobody uses the classical definition in their day-to-day practice, but it is important to know where everything is coming from. Yeah. So this is why we start with where things are actually originally defined. So for this, we have to introduce a function capital F, which is related to our small f. This is also a distribution function. And this is a function of capital Xi. So remember, small xi is the velocity. Yeah? And capital Xi is something that we call the velocity frequency. And this capital F is the bidirectional Laplace transform of f of xi. So I hope this is nothing that makes you now run away, because when you run away, nobody else can run away. I don't know how familiar you are with integral transformations. Yeah, so you can use a Laplace transform for the for usually for solving linear differential equations with constant coefficients. That's very useful for this. Usually there you use the one-directional Laplace transform. The bidirectional Laplace transform is basically a Fourier transform just where you take the variable in, where you consider the variable to be complex without writing I times omega. So here we have, because in the Fourier transform you have I times the frequency, yeah, and here we say we have the frequency xi, which is complex, yeah, but the complexity is, so to speak, hidden inside. I mean, the imaginary part is inside this variable. So we just take this as an algebraic quantity here. So we can also do the same thing with the Fourier transform. It's just a convenience thing. There's no difference in the final result. So, and we define this, by the way, unfortunately, it's the, okay, there is something that is a little bit unfortunate, according to the definition. So, but there are many these things in kinetic theory. For example, the ether, the function is the inverse of the entropy, so they have the wrong sign. And here with this Laplace transform, we also have the wrong sign. So actually, it's not the Laplace transform, but the inverse Laplace transform. Okay, but this shouldn't bother us. This is simply a question how the first guy who did this decided to do it. Yeah, so it's left-handed or right-handed. Yeah, so, and it of course it leads to confusion, because you always have to take, okay, it's the Laplace transform, but it's the inverse Laplace transform. It's with minus, not with. So the minus step we have here, and I agreed that I've done this in many of my publications in the wrong way. There's a minus in this exponent, yeah, just for consistency. So the Laplace transform, so, oops, I have to, this is, so we introduce the Laplace transform in the velocity space, three-dimensional, where we have to introduce then a velocity frequency, yeah? So, or transformed the Laplace transform of the velocity. Actually, I prefer to say this is the Laplace transform of the velocity, because the velocity frequency, well, is hard to imagine what this would actually mean, yeah, but say these are just other variables. So this is xi, and again we write this as capital Xi, so this vector capital Xi and capital Epsilon. I'm very sorry that I cannot beautifully write this, and the capital Zeta, yeah. So the Zeta is the same thing with ether. It looks like a different Latin letter, but this is why it's usually not used in the capital form. But we'll use it this way. So from this Laplace transform, we can derive all our moments, and this is why this is called the moment generating function. By the way, you can apply everything here not only to kinetic theory, but to distributions in general. Yeah? But here we need this, of course. Okay, so moment generating function, how does this work? Yeah, we define a moment in A, B, C. So we come to these indices, and they are defined by taking the derivatives of this frequencies. So the 8th derivative of the frequency xi, the beat derivative of the frequency upsilon and C derivative of zeta on f of xi, and we use a development point, namely xi equal to 0. So we take this function, yeah, take the derivatives, and then evaluate it at 0. This is what it means. And this gives us the moments. So this is nothing else. I mean, if you look at it, yeah, you have a development point, and you take derivatives at this development point. From where do you know this? How? What is? You have seen this. Very basically.
I did not understand it.
So okay, you want to represent a function by taking it at one specific point and taking derivatives of this. Where have you seen this? We make a Taylor series.
Okay, yeah.
Yeah? So the Taylor series represents the entire function if you have infinitely many derivatives. And this is what we are doing here. Yeah? So the moments are these coefficients of the Taylor series. So what we're doing is we're doing a Taylor series of this function. Yeah? And the coefficients of the Taylor series, these are the moments. So unfortunately, I'm not allowed to write, again, this is again something with definitions, which is annoying. I'm not allowed to write Taylor series because the Taylor series also has a factor in front of it, an actually arbitrary factor that we here skip, right? So 1 over something factorial. Yeah, so this is the one thing that we would have to add in order to get the real coefficients of the Taylor series. But what we have anyway, so I expressed it a little bit differently. We have the coefficients of a series expansion. Yeah. Of f of xi at the position, so this is our development point, xi equal to 0. So this is the original definition, and now comes the big simplification that everybody is going to use. You know, sometimes it's very important to know where things are coming from. So you should keep this in mind, and if things get unclear, you can always come back here and see, okay, this is where we originally came from. Yeah? In some cases, this is very important. Now, just for remembering, this is our velocity vector. This is xi, upsilon, and zeta. And now we introduce actually our, okay, I have to write these guys here again. So A, B, and now I write the integral from minus, I write the definition of the Laplace transform, f xi e minus xi, and this evaluated at xi, capital Xi equal to 0, and this integrated over xi. So what you see here is that the only thing that depends on this vector xi, yeah, is this guy here. Yeah? Meaning that you can take this derivatives and put them into here, yeah? And taking the derivative of an exponential function is pretty simple. This gives you a polynomial, and later putting 0 into the exponent will give you 1, right? So this means what you can simplify this integral to give you something much simpler, namely the integral from minus infinity to infinity on f xi, and what is left is xi, sorry, not vector, xi by the power of a, upsilon by the power of b, and theta by the power of c, the xi. Okay, so and this is where people usually start. So this is the definition. You can define moments like this, yeah, but I've told you where they originally come from. So this is how they simplify. Now, we call this guy here, we call this guy in particular, sorry, I have to write proper, countable raw moments. So why are they countable? They are countable because they have counters. And these counters are A, B, C, right? So you can count them up. Yeah? So by putting, they have a 0, first, second, and so on. And they are raw because they are in the lab frame. And of course, this is not absolutely required, but you can take, say, this is your kernel for the moment, and you can now arbitrarily define different kernels, and then they look in a different ways. They look differently. So moments can be defined in many different ways, and indeed they are. So everybody who thinks that something is important for them does it in their own fashion, fortunately. So they can be differently defined, for example, with regard to the frame of reference. This is what we meant by lab frame. Also, we can take different orthogonalizations, orthogonality conditions. This is actually something that is not, this still requires some sort of research. It's still not completely clear and accepted by everybody, I believe. And then you can also normalize moments in different ways. So, for example, you can have a first moment that is the momentum, or you can have a first moment that is the velocity. So if you normalize, if you divide by the mass, then you get velocity out of this moment. Okay, let's first look at the frames of reference. So because this is a big and important one. So frames of reference. So usually we distinguish between two obvious frame of references. So there are there are infinitely many different frames of reference. Yeah, but we focus on two. And the first one is the Eulerian, and the other one is, as you just said, the Lagrangian. So, Eulerian is what we call the laboratory frame. This is the frame of a stationary observer. And the moments that we derive in this lab frame with a stationary observer, this is what we call, or what has become called raw moments. By the way, this is not these are not necessarily the only names. So you may also come across different people will give these things also different names. But in this lecture, in bigger part of the Lattice Boltzmann literature, we call these guys here raw moments. And the other one is the material frame. And this is moving with the flow. So the observer is moving with the flow, and these guys are called central moments. Okay, so very simple picture for getting the difference. Say this is our distribution f, and this is our velocity xc, and this is, I don't write a vector because now it's one-dimensional the way I draw it, and suppose our distribution function looks like this. Because there is an average velocity u, and this here is xc equal to 0. Yeah? So the distribution is not centered at xc, but I can define a new distribution. Let's call them, how did I call it? F and a snake. Yeah? And this is related to the velocity u. Now for this, I can apply a Galilean transformation. So that my f u with the snake of xc is equal to the original f expressed at xc plus u. Yeah, this is just the transformation of the variables. And of course, we can now also use this in our original definition of our moment generating function. Where we have f xc plus u e xc times capital Xc, and this integrated over xc. Now, because this is an integral from minus infinity to infinity, so it has no bounds, what we can do is we can shift the entire thing inside the integral. Very simple. Yeah, we shift this because the bounds will not change. So I shift this by u. When I shift the f by u, I have to shift the other guy by minus u. I have to shift the other guy by minus u. And now I have this here in the exponent, And if I now do the evaluation of this again for deriving moments, yeah, the way we simplified before, you get an equation for the central moments, central countable moments. It looks like this. So I will usually write central moments with K. It's an old tradition. It's not everybody is doing this. KABC now becomes the integral from minus infinity to infinity f xc. Now we said what is in the exponent comes down, right? So this will now become xc minus ux by the power of a, upsilon minus uy by the power of b, and zeta minus uz by the power of c dxc. Okay? Clear, right? So and these are now de-shifted moments, so they are centralized. So you can shift them to any other frame of reference, but we have chosen a specific frame of reference, namely the one that is centered. And because it is centered, leads to the following, so to speak, definition. So ux, uy, and uz are defined such that k100 is 0. Yeah? Clear? No, not because y and z are 0, but because we shifted our coordinate system such that the distribution is centered, yeah. Right? So, and then they have the same amount of particles on the left-hand side and on the right-hand side. So in this frame of reference, the velocity, because so k100 is, okay, if it's not normalized, then it's the momentum. And the momentum in the frame moving with the fluid is always 0. Yeah? No momentum. This is right. This is 0. K 010 is 0, and K001 is 0. So these are the so-called first central moments, and they are by definition they are 0. Otherwise, it's not central. Okay. So then there is also at least one moment, the density moment. The density is Galilean invariant. So we call things Galilean invariant whenever, should write this capital. So if you measure a quantity in one frame of reference and in a different frame of reference, and you always get the same result, no matter what the frame of reference, this is what we call Galilean invariant, right? So this is a Galilean invariant thing. And this is what we call zero moment. So what you could probably guess now, we distinguish moments, especially countable moments, by their order. So the order of a moment is the sum of its indices. Well, I don't know whether I should write okay, I should write indices. There's indices and indexes. I don't know what is the proper word. So the sum of the indices is A plus B plus Z. So this is what we call their order, right? So for example, we have how many second order moments do we have? Can you make the guess? So we have M200, okay, I should write this capital. I'm always, literature is not consistent, yeah, so I'm also not consistent with writing this large or small. M0, so these are second order moments, and then we have mixed second order moments. 110, M101, and M011. So we got 6 of them. And of course, we have all of them also in terms of central moments, yeah? Oh, when I asked you, I've already written it down. Okay, let me see 2 more things. Let's write down the temperature in raw moments. Just to see what, so to speak, as an exercise. Temperature in raw moments, I always have to, okay, so now it always depends a little bit the prefactors that we use for the in the kernel of the moment definition always depends a little bit on how we interpret F, yeah, whether this is what unit it has here. So I take now out M, this is the mass of one particle, divided by 3, rho, by rho I mean the particle number density, so it's particles per meter cube, and this into the Boltzmann constant. Yeah? So, but don't be too confused about this units. So it's more or less the basic idea behind this. So basically, what we do is we put some constants in front of it in order to get the right units. Yeah? So this is the integral over f of xi minus u, and this square, where the square of a vector is the scalar product of the vector itself. Right? So, and now if we go on and expand this, and I hope I am not miswriting this prefactor. So we have f of xi, and if we expand this, we have xi times xi minus u times 2 u, so this is, what is it, the binomial, what is it called, binomial equation? Yes. Binomial expansion, yeah, I guess so. So now this can be now also written in all its components. In order to understand this, I'm only doing this once here for demonstration. So all its components would be xi square, upsilon square, zeta square minus ux xi minus 2, yeah, minus 2 uy upsilon minus 2 uz zeta plus ux square plus uy square plus uz square, and this integrated over xi. Okay, so now the important thing why we are doing this is to see that the xi, so the Greek variables are the ones that we integrate over, and the Greek, the velocity, the Latin ux and so on, they are the ones that we do not integrate over. Yeah, they are constant for this purpose here. And if we do the integration, what comes out, this here is a second moment, this is a second moment, this gives a second moment, and this thing here, this gives first moments, right? So we get again the same prefactor, which I'm going to ignore now, and this goes into M200 plus M02, which is this one, plus M002, which is this one. Now minus, as I said, we get ux is constant, and this guy here is the first moment, M10 minus 2uy M010 minus 2uz M001 plus, so what are these guys? Yeah, the integral is now over 1. Yeah, so 1 is giving us the zero order moment. So it's M00 ux square plus M000 uy square plus M000 uz square. And that's it. So now what we need to know is that M000 for non-normalized moments would be the particle density. M100 is non-normalized, so rho, sorry that my rho's look the same like my zetas, yeah? Rho ux, yeah, first moment. M010 is rho uy, and M001 is rho, that should really be more beautiful, uz. So, and if we now what you now see is that if you take, say, this guy here, you will put this into this guy here, yeah, and then it will partly cancel with this guy here, right? So let's see what is coming out. So we get m divided by 3 rho Boltzmann constant. So what is left is M200 plus M020 plus M002, and the rest part we can actually get together as, again, vector product with itself, so all the components times rho. Yeah? So now what you see here, this is the second raw moment minus what you basically have here is the kinetic energy. Right? So this is drawn out. Now in central moments, obviously without doing it, I mean, you can immediately tell me how this is going to look like if what I told you was true. Then this is K200 plus K020 plus K002, and what else? Okay, and what is the kinetic energy in the centered frame of reference? Zero, right. So that's it. Okay, so we have one more we have one more thing to cover. Now we have this was the frame of reference, and now we have the orthogonality, which is a bit of a topic that generates sometimes headaches. And with this, I have to say this sometimes generates headaches among these people who research this stuff for 30 plus years. Okay, so in case you get, I mean, I don't want to discourage you, but in case you get a little bit confused, then don't take this as a reason to stop here. Right? Yeah. This is why I write orthogonality and the long search for independence. So many people want to be independent. And here moments should also be independent. Now the big problem, maybe as in politics, right? The big problem is, what do you mean by independence? Okay, let's ask one question. Yeah. So we have different moments. We have infinitely many moments. And the question is whether these moments carry different information. Or whether they all carry the same information, which could also be. So, now, looking at the distribution in general could be difficult. This is why we look at the simplest distribution that we can imagine, and this is, of course, the equilibrium distribution. Okay, let's look at the equilibrium, and at the equilibrium, let's see whether we get different information from different moments. So, say our equilibrium function looks actually like this. Now I've not completely introduced all these factors, but say they are not, okay, so this is not absolutely important why you have these factors. This is just factors in order to make them, get a level of consistency. So the important thing here is in the exponent, where we have xi times m, yeah, divided by 2. This is the kinetic energy, yeah, and this is the and kBt, yeah, this is of course also the thermal energy. So this is why they. So this is the transformation, so to speak, yeah, from kinetic energy to temperature. This goes by kb. So, and this would be the distribution function of a gas at rest. Say so, and now if we take, for example, our moment m2 0 0 equilibrium. From minus infinity to infinity, so we get again this prefactor 2 pi k Boltzmann T divided by m. By the way, this rho is again the particle density, it's not the density including mass. This goes to xi times xi. These things are not always written in the same way. You can use the Gauss constant, yeah, you can use mass-reduced Gauss constant, which is often used in kinetic theory, so they unfortunately will not always all look the same. Okay, so I've just forgotten something. So this is the distribution function itself, and now in order to get this moment, we have to multiply by xi squared, right? So this is how we get that moment, right? This is how we learned it. And we integrate this now over xi vector, yeah? Don't confuse this. Xi now is one component of this vector. This is why it's not a vector, yeah? Xi squared, that one here. And here we integrate over the entire velocity space, so over all three directions. So I used Mathematica, so because I'm too stupid to solve this, so I used Mathematica and this gives me this result, okay? As we would expect, it depends, it's basically some constants or things that we have to scale out times the temperature. So the second moment is supposed to be related to the temperature, right? So now let's look at, for example, the forced moment. So how does the forced moment look like? I have to make sure that I get this here right, because I often write these things wrong. So xi times xi m divided by 2k Boltzmann t, and now it's a forced moment, so this will be xi by the power of 4, right? So the xi, again, the vector, and using Mathematica to solve this is we get 3 rho k Boltzmann t divided by m and the entire thing here squared. Okay, now does this contain new information? No, it contains the same information in a different way. Temperature squared. And this is a big problem with many of these moments, so you see the same information popping up again and again. And this is something that you usually don't want, and for this you derive moments in a different way. Okay, let me just write down here my sentences, because I'm still in hope that some of your colleagues will actually download the sheets at least and learn it this way. So, often we are interested in different information. So, in principle, all the moments, they are, say, now they are not necessarily orthogonal to each other, but they are linearly independent. So, if there is further information, this can usually be extracted from these moments. However, there is always a mishmash of this information. Yeah? So this first order moment already includes some temperature square, and it may, if it's not in equilibrium, it may also include something else. Yeah? But if you want to know this something else, you first have to get rid of this temperature part. Yeah? And this is inconvenient and causes all sorts of mathematical problems if it's not dealt with correctly. So now the motivation here is that it is often necessary to make information independent of each other. And this is usually attempted by orthogonalization. And the trouble with this is that this is not completely unique. Yeah, and so I am just warning you that this is a method that has some problems, and we'll later come a little bit to the problems, but let's first see what it actually does. So let's say we have two different moments, and the first one I call M, and I take the moment over a distribution, so this doesn't need, this in general has nothing to do with kinetic theory, so it's completely general. We take a moment of a distribution and we do this by a kernel phi m, and okay, because we are in kinetic theory, we call our variables xi, right? And now say we have a different moment and we call this n, and this has a kernel n, of course. So we define these two moments, and now we say that the moments with these kernels phi m and phi n are called orthogonal with, now comes something very important, with weight w, which is a function of xi, if the following holds, namely that the integral over the entire space in w, xi, phi m, phi n, the xi is equal to 0. So this means orthogonality given the weight w. Now, there you will find definitions of orthogonality, unweighted orthogonality, by assuming that w is 1. Yeah? And now you can define, so this is my orthogonality. Yeah? So, and don't think about it anymore. But you will run into some trouble if you believe that this is the orthogonality and this is all that there is to orthogonality. So you have a weight function w, which of course can be 1, but what is orthogonal depends on w. Yeah? This is very important. Now the idea, the hope, yeah? If m and n are orthogonal, they extract independent. You know, the trouble is we've not properly defined what independence is. We'll come to this in a later lecture. Information from the distribution. Okay. You know, this is the subject that we are teaching here is not such a mature subject that you should consider me, so I tell you how it is, and you know, and everything here is done. Yeah. So in this subject, there is still an ongoing battle on how to what independence means, what we want to obtain with this, and how we define it. So, of course, I'm always told off that I should not scare students by telling them that things are not clear. But on the other hand, I simply refuse that if something is not clear, that I pretend to you that is completely clear, and you go out and believe I told you the absolute truth. Okay, so this is not the case here. No, so what do people do? Right? So there is the first, so we look at one way of orthogonalization, and this is the Hermit moments, and this is one of the ways that actually make a little bit of sense. And there is in literature a lot of stuff that does not make sense. So the idea behind the so-called Hermit moments is that we use as a weight function the equilibrium. Yeah? If we use the weight function, the equilibrium, then the dependence that we saw between the second moment and the first moment in the equilibrium will disappear, right? And we wouldn't have, again, just this problem that the temperature, that the first order moment, again, contains the temperature. So this would then disappear. And this means we make moments independent at equilibrium. So this is something that's also used in Lattice Boltzmann. So if they are independent in equilibrium, so the idea is that they are close, say close to independent, as long as we are near equilibrium. So suppose we never go far away from equilibrium, then this can still be a good approximation, and this is basically the idea behind this. So the equilibrium is a Gaussian, right? The equilibrium is Gaussian. So F equilibrium should be proportional to an E by minus x squared. So now this is now general, right? So say one-dimensional x, yeah, distribution, where this sigma now is simply the standard deviation, and x is the random variable. So again, this does not necessarily have anything to do with the Boltzmann equation. So this is, of course, Hermit moments can be derived for anything, yeah, in particular for things that are close to a Gaussian. And what we have here is a distribution that is close to a Gaussian. And this is called Hermit moments because they're using Hermit polynomials as kernel functions. So the kernel function phi n of x and sigma, so n is the order of this, is minus 1n e by the power of x squared by sigma squared, and comes the derivative dn by dxn e minus ex squared sigma squared. Okay, so this is, do you see that this is a polynomial? Not right now, right? So if you take derivatives of the exponential function, you get a polynomial, and then you are left, so this will always be there, and this has a minus here, and here we have the same thing without a minus, so they, at the end of the day, they will cancel out, okay? So, and what is left is the polynomial. So these guys are the Hermit Hermit polynomials of degree n. So n is the one here. And if we execute this, we see that phi is 0, so 0 order is 1. So what you would expect from a 0 order polynomial. Phi 1 is 2x divided by the standard deviation. Xi 2 now is minus 2 plus 4x square divided by sigma square. Yeah, and this is now going on and on. So these are the Hermit polynomials in one dimension. For kinetic theory, we need them in 3 dimensions. So we get the multi-dimensional Hermit polynomials by so-called factorization. So factorization is simply the idea. Now we have a 3-dimensional kernel function, NML, and this is a function of xi by sigma, upsilon by sigma, and zeta by sigma, and this is simply phi n, so the 1-dimensional case of xi by sigma times the 1-dimensional case m of upsilon by sigma times the 1-dimensional case L zeta by sigma. So, and of course you can also have these now in central Hermit moments. This is simply phi with this snake, NML, xi, sigma, upsilon by sigma, and zeta by sigma equal to phi. So now this we simply get by subtracting, yeah, by moving again this moment into the frame of the Gaussian that we observe. So I forgot the n here. Phi m upsilon minus u y by sigma and L phi L what is it? Zeta minus u z by sigma. So, okay, we're running out of time, but I have just the 2 sentences I want to write down now, is that the conserved central Hermit moments are 0, and all non-conserved served central Hermit moments of the equilibrium are 0. So this means we can use this Hermit moments, in particular when we are close to the actual equilibrium, we can detect deviation from equilibrium by looking at these Hermit moments, yeah, because each Hermit moment gives us a deviation of the distribution function from its equilibrium state. Okay, so basically this is the lecture from today. I hope that everybody who was not attending in the class will attend online, and then probably more people come to class next week in order for us to be more able to ask questions here. Yeah, thank you for listening. So I have to turn this off somehow.